Today we're going to go over the gas laws we already know and review them, and then we're going to introduce the ideal gas. The first law is Dalton's law. Dalton's law is simply that the total pressure is equal to the sum of the partial pressures. By way of example, we can look at the air we breathe. The air we breathe is made of nitrogen, oxygen, and argon. Those are the primary constituents, and of course a bunch of other things that are very much lower. If we look, we can see that the nitrogen concentration here, or partial pressure, is about 0.781 atmospheres. The oxygen concentration about 0.21 atmospheres, and argon a little bit less than 0.01 atmospheres. If we add all those together, we get 1 atmosphere pressure. Now, if we wanted to try and graph this on an XY graph, we'd run into a little bit of a problem. We really don't have an independent and a dependent variable because this is just a sum. So a bar graph is actually much better for graphing this. If we look at the total 1 atmosphere, right up here, we've drawn a line to show that we have to equal this total. And then we look, and here we've got the nitrogen, which is our 78% of that, 0.781. And then the oxygen is the 0.210. And then lastly, we've got a little sliver of argon right up here at the top, which makes up about a little less than 1%, 0.009 atmospheres. And they all total the 1 atmosphere. So here we're just summing up pressures to get a total. We could also solve for a missing pressure if we already knew the total. Next is Boyle's law. Boyle's law relates pressure and volume. So the conditions of pressure and volume at condition 1, when we multiply them together, are equal to the product of condition 2. If we look at this animation, we can see in the animation that we're increasing the pressure up here when we add weights to this piston. And that pushes the piston down and compresses the particles and results in the pressure going up over here. Notice that the temperature here remains constant at 300 degrees, and the mass, or moles, is also constant. We're not adding anything. So when we look at our graph, we can see that the graph is going down, and this is an inverse relationship, because as 1 goes up, that would be the pressure increasing in this direction. The volume is going down like that. So we have an inverse relationship. The next relationship is Charles' law. Charles' law relates volume and temperature. So we have V1 over T1 is equal to V2 over T2. If we look at an animation here, we can see that the pressure remains constant and the mass, or the moles, also remains constant. So the only thing that's changing is temperature, and that's having an effect on our volume. We're changing the temperature with this little fire down here. We're adding some heat, and when we add heat, this temperature right here goes up, and we can see here that this relationship is direct, meaning as the temperature goes up, the volume also goes up. Next, we have Avogadro's law. Avogadro's law relates the volume to the number of moles, and this is our common sense law that says that the more stuff we have, the bigger it is, the more space it takes up. And if we look here, we can see we've got this plunger going, this like a bicycle pump, and it's pumping more stuff in to the container, and so the volume of the container is going up. The reason the pressure isn't going up, the pressure is constant, but the reason the pressure isn't going up is because this top part is able to move, and the weight on top is the same. So the pressure is the same. Anytime we have an expandable container, like a balloon or a bag, the pressure is going to remain constant, and the only thing that we can change here is the volume, and we're doing that by adding moles. Our previous one, we were adding temperature, but in this one we're adding moles. And when we do that, we see again that we have this linear relationship here, where as the moles goes up, we're also increasing the volume. So this is a direct relationship right here. The hypotenuse of this triangle is a direct relationship. Now the combined gas law, we learned this one. The combined gas law puts together all the gas laws as well as another one, and we end up with a relationship between pressure, volume, moles, and temperature. And this came about because the product of these two divided by the product of these two was a constant, which meant we could look at the pressure, volume, moles, and temperature at one set of conditions and then determine another set of conditions, or at least one variable at another set of conditions, because we knew that these two had to equal each other. Now, if we wanted to graph this, we can't do it. We can't graph more than two variables. So if we got three or more variables, we're stuck, and we can't graph it, at least not on a two-dimensional graph that we have right here. So now that we've reviewed and covered all the ones we've done so far, let's take a look at the ideal gas. An ideal gas, as a review, is an imaginary gas that conforms to all of the assumptions of kinetic molecular theory. And there's really no such thing. But real gases, they don't conform. But sometimes a gas temporarily conforms to most of the assumptions of kinetic molecular theory. And then we can treat it like an ideal gas. This happens at low temperature, or low pressure rather, and high temperature. And the reason that happens is because the particles are far apart and they're moving too fast to interact. Now, at high pressures or low temperatures, that's when gases begin to look kind of like liquids, and so they're not ideal. But truthfully, the air we breathe is pretty darn close to ideal. Most of the conditions that we're going to look at in chemistry class are ideal, so we can use the ideal gas law for those. Now, we've already learned the combined gas law. P1V1 over N1T1 is equal to all of that stuff, but with twos. Both sets of conditions are equal to each other. The combined law came from this fact, the fact that the pressure times volume divided by moles and divided by temperature always works out to a constant value. And if it works out to a constant value, then that means another set of conditions will work out to the same constant value, and we can set the ones equal to the twos. But there's something else that we can do with this. If we know one set of conditions that are always true, we can figure out what this constant is right here. And what this constant is going to be kind of important. So we can determine what the conditions are at one set of conditions. Those are standard conditions, STP, that stands for standard temperature and pressure. Standard pressure is 1 atmosphere, or we could use one of the other sets of units that we've learned. And standard temperature is 0 degrees Celsius, or 273 Kelvin. We can add the 0.15 if we need a little more precision. Standard volume, or the volume of a mole of gas at standard temperature and pressure, is 22.4 liters. And lastly, we said that 22.4 liters was for 1 mole. So if we take all of these variables, 1 atmosphere, 273 Kelvin, 22.4 liters, and 1 mole, we can combine those and calculate what this constant is over here. So let's do that. We'll substitute in 1 atmosphere for pressure, 22.4 liters for the volume, 1 mole for the moles, and 273 Kelvin for the temperature. And when we do that, we get this number, 0.0821 atmospheres, liters over moles, Kelvin. Why did we get these really screwy looking units over here? I mean, this looks like a mess. Well, the reason we got it is because we had 1 atmosphere right up here. If I can draw, we had 1 liter here. Underneath we had a mole, and underneath we also had a Kelvin. So we've got all of these units and none of them cancel. So we end up with this constant over here, which we call R, and this is the ideal gas constant. We can use this to calculate any of these other variables if they were missing. So imagine if if our volume was missing, we could figure that out if we know what this constant is. Now, this constant can be found in many different units. I've got 3 here, but there are dozens of different unit combinations that we could come up with. The first one, which is the most commonly used one in our field of chemistry, with the sets of units that we use, is 0.0821, because the units are atmospheres times liters divided by moles times Kelvin. This is most common for us. But if we have other units like millimeters of mercury or kilopascals, then we can use these other values for the ideal gas constant, and that way all of the units will cancel. So when we rearrange that equation, P1V1 over N1T1 is equal to R, we get this equation. And this is the equation for the ideal gas law. Remember, we were looking at the P and the V divided by the N and the T to get R. But if we rearrange it, we end up with this straight line right here, which is much easier to work with when we're trying to solve for a variable. The P stands for the pressure, the V for the volume, which for us will always be in liters. N is the number of moles, R is our ideal gas constant, and T is the temperature, which is, of course, in kelvins. When we're looking at a word problem, it's easy to spot an ideal gas law problem because there's only one set of variables. We've only got one P, so we don't have a beginning pressure and an ending pressure. We don't have a starting volume and an ending volume. We've got only one set of these variables, and that tells us it's an ideal gas law question. Let's look at an example. The first example is, how many moles of gas are there if there are 120 liters of sulfur dioxide at a temperature of 40 degrees Celsius and a pressure of 1.85 atmospheres? So we're going to use this equation, PV equals nRT, the ideal gas law, and we chose it because there's one volume, there's one pressure, there's one temperature, and it asked us for moles. So these are our starting variables. We have pressure, volume, moles, the ideal gas constant, and the temperature. Now, the temperature originally was given to us as 40 degrees C, but we know we can't use C. We've got to use Kelvin, so we add 273, and that gives us the temperature of 313 Kelvin. We start with this equation, PV equals nRT, but we want to solve just for the value for N. So how do we do that? Well, we're going to have to divide this side by R and T to get rid of them on this side. And if we divide this side by R and T, then the R will go away, the T will go away, and we'll have moles all by itself. But that means, of course, that we have to divide the other side by R and T to do that. And when we do, we have this equation. N, that's this one over here, now is equal to PV over RT. It's very easy to substitute now. We substitute our P right here and our V right here. R, complete with this big messy set of units, and then finally our T. Well, why do we substitute with this great big messy set of units right here? And the reason we do is so that they'll cancel and leave us what we want. The atmospheres in our volume or in our pressure cancel with the atmospheres in R. The liters in the volume also cancel with liters. And our Kelvin down there on the bottom cancels with that other Kelvin. And the only thing that's left is moles. So those are our units. And that's what we were asked for in our question. It says how many moles, and that's what our little N here is. So we end up with an answer, 8.64 moles of sulfur dioxide. Notice that I rounded this to 3 significant figures because I had 3 significant figures in my pressure. Let's look at another example, which is a little bit more complicated. Here it says, what is the pressure? And then it tells us the pressure units it wants. Millimeters of mercury, exerted by 85.5 grams of carbon dioxide at 27 degrees Celsius if it's in a 15-liter container. So first we have to identify our variables. Pressure is our unknown. Volume is 15 liters. But what about moles? It did not give us moles. What it did give us was grams of carbon dioxide, and we need to convert that to moles. So this is just a real quick little stoichiometry grams to moles conversion. So all we need is the molar mass of carbon dioxide, and we do that, and our grams cancels with grams, and we divide, and we end up with 1.94 moles of CO2. So that's what we'll use for moles. Now R, we started by using R right here, 0.0821. But notice the units. The units are atmospheres. And up here, it asked us to convert into millimeters of mercury. So we could use this value for R. We could, but then our answer would be in atmospheres, and we'd have to convert it. So how about we use this value for R, because the units are already in millimeters of mercury. And so we can ignore this value for R, and we'll use the other one. Our temperature, remember 27 degrees C, we cannot use C. We have to add 273 to it, and so our temperature is 300 Kelvin. We're going to start with this equation. Remember, we're solving for pressure. So to solve for pressure, I need to get rid of volume. So if I divide by volume, then the volume will cancel out. But that means I need to divide my other side also by volume. And that leaves me with the pressure is equal to nRT over V. So we end up with this equation. Pressure is equal to nRT over V. If I do my substitution, here's my 1.94 moles. Here's my value for R, 62.4, with all of those associated units. Here's our T, and underneath is our volume. Let's look at those units. The moles cancels with the moles in the R. The liters in the R cancels with the liters down below. The Kelvin in the R cancels with the Kelvin, and it leaves us with millimeters of mercury, which is just what it asked us for. What is the pressure? And our answer is 2,420 millimeters of mercury of carbon dioxide. Now, right here, I have three significant figures. This 0, while it is important, it is not significant. It's a placeholder. But we've got three significant figures here in the front because our volume here had three significant figures, and so did our grams. So that meant that our moles had three. So we've got three sig figs. So we've got three sig figs here. So that's how many we need to have in our answer.